Hello everyone!
Today we're here to talk about balancing chemical equations, drawing Lewis structures, molarity, and gas relationships.
In other words, we're going to be talking a lot about reactions, but not just the fun reactions in a middle school.
Like mixing vinegar and baking soda.
We're going to be doing all the math behind these reactions that keep us alive.
Most specifically, we're going to talk about the oxidation of ammonia, or NH3.
Before we get started, we need to predict the products that these two reactants will yield to.
We know that when ammonia reacts with oxygen, it will produce nitrogen oxide. We can also assume that the remaining two elements will react to form H2O, or water.
Nitrogen monoxide is going to be a gas. So we write a G in parentheses, and we know that H2O is going to be in liquid form, so we write an L. But wait, Jade, the equation's not balanced.
Oh, Granny, you're right. In order to balance it, we should list out the elements on both sides and add coefficients where we need them.
First, we list all the components on both sides and write down how many atoms of the element we have. Nitrogen has 1, hydrogen has 3, oxygen has 2. Then on the product side, nitrogen has 1, hydrogen has 2, and oxygen has 2. As we can see, hydrogen is the only one that is not balanced.
Therefore, we need to start adding coefficients in front of the components so that we can get the same amount on each side. We have to do this due to the law of conservation of mass, which states no matter can be created or destroyed.
Now we can put the coefficients in front of hydrogen on the product side in order to make it equal to the hydrogen on the reactant side. However, by doing so, we are also adding a coefficient in front of oxygen that is in H2O. We can add a 6 in front of the water molecule, add a 4 in front of ammonia, in order to get a total of 12 hydrogen atoms on each side.
We'll also have a total of 7 oxygen atoms on the product side and 4 nitrogen atoms on the reactant side. The way to solve this is to add coefficients in front of the oxygen gas and nitrogen monoxide. Therefore, we can add a 5 in front of the oxygen gas to give us a total of 10 oxygen atoms on the reactant side, and we can add 4 in front of the nitrogen monoxide to end up with a total of 4 nitrogen atoms and 10 oxygen atoms on the product side.
Ta-da! We're done. Now the equation is balanced. We have 4 nitrogens on each side, 12 hydrogens on each side, and 10 oxygens on each side. Nitrogen has 5 valence electrons, and each hydrogen has 1, but we have 3 hydrogens. So in total, there's going to be 3 valence electrons for hydrogen. In our Lewis structure, nitrogen is going to be the central atom because it has the most valence electrons, and all the hydrogens will be plotted around it. As we can see, there is one valence electron allocated to each hydrogen, making it have a formal charge of 0. However, nitrogen is still missing 2 valence electrons, so we can easily plot them right here, without the need to add another bond. That way, the formal charge of nitrogen is 0, and our Lewis structure is complete.
Now we will be doing the Lewis structure for the diatomic molecule oxygen. We know that oxygen has 6 valence electrons. However, since it's a diatomic molecule, there are 2 oxygens, which will give us 12 valence electrons in total. We can first start out by drawing 2 oxygens, bonding them together with a single bond. We can then go around adding the valence electrons. However, each oxygen has 7 valence electrons now, when it actually has 6. Therefore, we can remove a pair from each of the oxygens to then create a double bond. Now we can check. Each of the formal charges is 0, therefore this Lewis structure is correct.
The third thing that we need to do is find the limiting reagent. Let's say that you're given 5 grams of ammonia and 12 grams of oxygen. Which of these two is the limiting reagent, and which of these two is going to be in excess when used in a reaction? In order to find the limiting reagent, we can use a proportion. We know that we have 4 NH3s and 5 grams of it. We also have 5 oxygen atoms, and let's say we have X grams of it. The reason we put X is because we're trying to find how many grams of O2 is needed with 5 grams of NH3. But then we cross multiply and find out that the answer of X 6.25. What we can see from this is that we have a lot of oxygen remaining, since we only need 6.25 grams of oxygen to react with 5 grams of NH3. Therefore, we can conclude that NH3 is the limiting reactant.
The next part of the problem is to find the mass in grams of each of the products. The product is what we have here, which is 4 nitrogen monoxide and 6 water molecules. The way to do this is to first we need to convert what we have in grams into moles. We have 5 grams of ammonia and 6.25 grams of oxygen. We need to find this in moles. So, the way we do this is that we need to find the molar mass of NH3. In order to find this, we first need to find the atomic mass of nitrogen, which is 14.06, and the atomic mass of hydrogen is 1.01. But seeing as we have 3 hydrogen atoms, we need to multiply this by 3. Therefore, this all adds up to 17.09 grams. We can now do the same with oxygen. The atomic mass of oxygen is 16.0. And since we have 2, we now have 32 grams of oxygen gas. Now we need to convert these two quantities from grams into moles.
The way to convert grams to moles is by cross-multiplying and canceling out the units. If we have 5 grams of NH3 and the molar mass for NH3 is 17.09, like we found in the last slide, and we want to get 1 mole, all we have to do now is cancel out the units, grams, and as we can see here, we are going to divide 5 and 17.09. This is going to give us a total of 0.29 moles. Then we do the same for oxygen. If we have 6.25 grams of oxygen and the molar mass is 32 grams, we want to get 1 mole. All we do is cancel out the grams and divide 6.25 by 32 to give us a total of 0.20 moles.
Now that we have the 2 molar measurements for the reactants, we can now find the 2 molar measurements for the products by using ratios. The ratio from here to here is 5 to 4, and the ratio from here to here is 4 to 6. We can solve by using proportions. 5 over 0.20 times 4 over x. X is going to stand for the moles of NO, or nitrogen monoxide. We can now cross multiply, and this will give us 0.16 moles of nitrogen monoxide. Now we can do the same thing that we did for the nitrogen monoxide for the water molecules. We can cross multiply, and this will give us 0.24 moles of H2O.
The last and final step is to convert nitrogen monoxide and the water molecules into moles. We do the same as we did before, except this time we put moles on the bottom so we can cancel out those units. So we put 0.16 mole times 1 mole over the molar mass of nitrogen monoxide. The molar mass of nitrogen monoxide is the atomic mass of nitrogen, which, as we said before, is 14.06, and the atomic mass of oxygen, which is about 16. We add those two together and we get 30.06. So we plug that in, cancel out the units, and we multiply 0.16 times 30.06 to give us 4.8 grams of nitrogen monoxide.
Then we do the same thing for H2O. We put 0.24 moles times the molar mass over 1 mole. To find the molar mass, we can times 2 times 1.01 plus 16 to give us a total of 18.02. We plug that in, and then we can cancel out the moles. And then we can multiply 0.24 times 18.02 to give us 4.3 moles of H2O. And those are the masses of the products in grams.
The last step that we have to deal with relates to gas laws. There are 3 components that go into defining a gas: volume, temperature, and pressure. To further understand this problem, we need to define what the relationship between these components is. As volume increases, temperature decreases. As volume increases, pressure decreases. As temperature increases, pressure increases as well. From this we can see that volume, temperature, and volume and pressure are inversely related. Or inversely proportional. While temperature and pressure are directly proportional. This question is asking us that if ammonia has a certain volume at a temperature of 110 degrees Celsius, what temperature is required to double its volume while keeping the pressure constant? In this problem, we need to take into consideration both the relationship that temperature has with volume and with pressure. Assuming that we're only talking about volume right now, if we need to double the volume, then the temperature has to be divided by 2. The reason for this is because the volume and temperature are inversely proportional, just like we defined earlier. However, if we do this, then the pressure wouldn't keep constant because pressure and temperature are directly proportional, just like we defined earlier as well. So the only way that this could happen is if we multiply the temperature that we are given, 110 degrees Celsius, by 2. I'll explain why. 2T is equal to 2P, and 2P is equal to 2V, because pressure and volume are directly proportional.
Now, we cannot leave 110 degrees Celsius as Celsius because when we are working with these types of relationships, our temperature needs to be represented in Kelvin. Luckily, this conversion is very simple. All we need to do is add 273 to 110. This will give us 338 degrees Kelvin.
As I stated earlier, the only thing that we have to do is multiply 383 degrees Kelvin by 2, and then we have the answer, which gives us 766 degrees Kelvin. The only reason why this problem was so tricky was because you need to find out all the relationships that gases have with each other.